Welcome back. So we said that we are going to explain why we want to maximize the margin. So let's take a look at this example. So here we have ham and spam, right? We have two classes. And this circle, right, the inner circle is actually the actual data point. And we have the outer circle, this is called the noise margin, right? So this is basically the noise margin, okay? So here we have, this is the actual classifier that we are going to use, or the actual boundary, decision boundary that we are going to choose. So any data point in this region will be classified as ham, and any data point in this region will be classified as spam. Okay, so here we have two dashed lines, right? So if you take a look at this dashed line, you will see that it's almost right on the closest ham point, right? And here we have the same case. This is the closest spam point, right? So we have, this is the other dashed line. So what are these dashed lines? These are the margins, right? So this is the margin from here, and this is the margin from here. And what we want to maximize is basically this margin, right? So from here to here, this is the distance we want to maximize. So what is the line that maximizing this distance? It's this line, right? This line is the line that we are going to choose. Why? Because let's say that this is the training data and this is the training data, okay? Now we have a new test point. Now if we have a ham point, most probably this ham point will be here, 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 anywhere in this region, right? But it can be also here, right? So using this decision boundary or this classifier, this ham point will be classified correctly. And if we have a spam point here, it will be also classified correctly, right? But if we use this decision boundary or this decision boundary, some of the data points in the test data will be misclassified. So all three lines for the training data are giving 100% accuracy. So we have 100% training accuracy here, 100% training accuracy here, and 100% training accuracy here. But this one is giving the best testing accuracy, because if we used this line, right, and we have a new ham point in the test data, and this ham point is here, right? So this way it will be misclassified, okay? And if we use this decision boundary and we have a spam point here, it will be also misclassified. So using this margin or this decision boundary, we are maximizing it. So we are generalizing the decision boundary, right? We are generalizing our decision. We are generalizing our machine learning algorithm, right? So this way, the testing accuracy will be closer to the training accuracy, right, than using this one or using this one. So that's why we want to maximize the margin. Now, let's take a look at the difference between hard and soft margins, right? But first, let's take a look at the margin equation. So as we said, this is the line we are going to choose, right? This black line. And we have two other lines, right? This and this. And how we choose this line or this line? We choose them based on the closest data point of either class. So here we have the first data point from the first class, and this is the first data point from the second class, right? So this is basically the line for class, let's say, +1, and this is for class -1, okay? And the equation of this line will be wx plus p equal 0, right? And the equation for this one is basically wx plus p equal 1, and this is wx plus p equal -1, right? And we want to maximize the margin m. M is the margin width, right? And these are the equations we just explained here, right? So if we do some mathematics and do some derivations, you will see that in order to get m, in order to get the margin, it's basically 2 over w, right? 2 over w. So if we want to maximize m, we cannot maximize 2. We cannot really change anything in 2. But what we can do is that we can minimize w, right? Because let's say w is 1, So this way m will be 2 over 1. Okay, so it's 2. Now let's say that w is 4. Okay, so we are increasing w. Now m will be 2 over 4, which is 1 over 2, so it's basically 0.5. Okay, so this way m decreased. So if we are increasing w, m will decrease. So if we want to maximize m, we want to minimize w, right? And w is basically the weights for x, right? The weights that we are training a machine learning algorithm, right? So we want to minimize half w transpose time w, right? This is basically, if we take this w and put it here, it will be like this: half w transpose w. Why half? Because we want to have the inverse of this equation. Okay, now this is called an optimization problem. So if we want to minimize something, we call this a minimization optimization problem. Okay, and let's define what we want to minimize as phi of w, right? This equation, we will say that this is phi. Okay, so this is called a quadratic function subject to linear constraints. So this is a lot of mathematics, and we are not really going to go deeper than this because this is out of the scope for this course. But I will leave you some resources if you are interested in the mathematics and you want to know the derivation of this equation. Okay, but this is basically called the quadratic optimization problem. Okay, and it's also called dual problem, and we use Lagrangian multipliers associated with every constraint in the primary problem. So if you are interested, you can check the resources and you will find the mathematical derivation for all this. But let's now look at the difference between hard margins and soft margins. So here we have hard margins. So hard margins is basically the margin itself. We cannot have any misclassifications here or any misclassifications here. We need to have all of them correctly classified. So any data point here, we cannot really have any data points here, and we cannot really have any data points here. But if you take a look at the soft margin, you will see that here this is the same margin, right? But we have green points here and we have also a red point here. So this is called a soft margin. So this is the difference between hard and soft margins. So hard margin requires all data points to be correctly classified. Okay, now what if the training set is noisy? So if we have some noisy data in our training set, then the kernel will be very complex. The function that we are going to use to have the data points from the lower dimensional space into the larger dimensional space or the higher dimensional space, this kernel will be very complex in order to fit all the data points correctly in the training data. So this will basically result in overfitting, right? So we will try something that is really complex in order to fit all the data points correctly if we use the hard margin. So that's why we mostly use the soft margin instead of the hard margin, right? So as you can see here, this is an example if we use the hard margin. So if we use the hard margin, then we will try to fit all the data points correctly. We don't really want to misclassify any data point. So as you can see, this is not misclassified, and this is not misclassified, and this is not misclassified. So by doing so, we used a very complex kernel or a very complex function in order to classify all the data points correctly. While on the other hand, we could just use something like this, right? We can have a line here, right? And if we use a line here, this will be misclassified, this will be misclassified, and this will be misclassified. But we will see that the distribution of the data is actually represented, right? We are classifying most of the data correctly, and this is the actual distribution of the data. Okay, so this is overfitting. So in order to allow misclassifications, so now using this equation, right? This equation is coming from here. So this equation is basically saying that we need to have hard margin. We cannot have any misclassifications. Okay, so how we can change this function m equal 2 over w in order to allow for misclassifications? we need to introduce a new variable, and we will call this variable eta. And if we introduce a new variable to an optimization problem, we call these variables slack variables, right? So we will add the slack variable called eta in order to allow misclassification of difficult or noisy examples, right? So here we have, if we have, this is our decision boundary, right? This is the first margin and this is the second margin, right? So as you can see, we have eta 1 1, we have eta 2, we have eta 7, and so on, right? So eta 7 is the 7th misclassified example, right? So we have a misclassified example here, we have a misclassified example, let's say here, right? And another misclassified example here, and so on, right? So this is how we basically define the new slack variables. So now, instead of minimizing this function, instead of minimizing half w transpose w, so instead of just focusing on w, we will also focus on eta, right? And in order to control how much we care about this term compared to this term, right, we will have c. So c is the most important hyperparameter in SVM, right? This is the hyperparameter that controls how much we care about correct classifications compared to how much we care about maximizing the margin, right? So this is the new formulation for the optimization problem. Instead of just half w transpose w, we have c. This is a hyperparameter summation of eta, right? So eta is the first misclassification, the second misclassification, the third misclassification. So k is the number of misclassified examples, okay? And we will sum all of them, right? Now, in the next lesson, we will discuss the c hyperparameter in more details. But in this lesson, you need just to understand the difference between soft margins and hard margins. So as we said, the actual equation or the original equation of the SVM, this equation is focusing on maximizing the margin without doing any misclassifications, right? So this is called hard margin, right? On the other hand, we want soft margins. Why we want soft margins? Because if we use the hard margins, then we will most probably end up with a model that is overfitting, because we want to classify all the data points in the training set correctly. So we will use the soft margin, and in order to introduce a new variable for the misclassifications, right, here we have 3 misclassifications. So we will have 3 etas, right? We will have eta 1, eta 2, and eta 3. And these 3 etas will be the misclassification. So that's why we have the new equation like this. And this c hyperparameter is controlling how much we care about this term compared to this term, okay? So let's go to the next lesson in order to understand better what do we mean exactly by the c hyperparameter and how it's used. So let's go.